having told in length about state equation in our previous lectures. In this lecture, we will talk about some other formulation methods for dynamic LTI circuits. In fact, we're already familiar with those methods, namely node analysis and mesh analysis from the LTI resistive circuits, and now we will generalize them to the dynamic case. Okay, so let's begin with node analysis. The idea is the same as was the case for LTI resistive circuits or resistive circuits in general. What we do is we write node equations, okay? That is KCL at each node, and we want to express the circuit in terms of the node voltages. So node voltages are our formulation variables, and that will be that will still be the case for the dynamic LTI circuits. So write down the current equations, KCL at each node, in terms of node voltages. Okay. Now let's remember our capital D notation. So what we have is df. So when we write this, we mean f being a function of time, we mean the time derivative of f. So d over dt f of t. And sometimes we denote this also by f dot. Now we will introduce the integral notation or inverse d notation. The inverse f, okay, by definition means the following. You integrate this function f starting from 0, which is our initial time, to the present time t. F tau d tau. Okay. So that's what we will mean by this d inverse. So although this is inverse operator, there is a subtlety that we have to be careful about, and it's this. Let me put it under remark, and it's easy to verify, so I leave that as an exercise. Note that d inverse f is f of t. In a sense, d inverse operates like an identity operator. However, d inverse d is not f of t unless the initial condition is 0. This equals f of t minus f of 0. Why that's so great follows from the definition. Okay, so we have to be careful in certain situations. Okay, now let's apply this idea directly on an example. And this is our circuit which we want to formulate in terms of node voltages. A third order circuit, we have 3 dynamic components. Excuse me. DC, I1, I2, and furthermore, this pair of inductors happen to be coupled with mutual inductance being 3 Henry. Okay? So what we will do now is we will formulate the circuit in terms of node voltages. Therefore, the very first step, or perhaps the 0th step, is doing proper labeling. Okay, so let's choose a ground node. And then what remains are these 3 nodes. The node voltage of this node is directly known, therefore it's not an unknown, it's Vs. Therefore we have 2 unknown node voltages, which will be our formulation where so let's call them EA and EB. Okay, now let's write KCL at node A and node B. Node A, this is our node A, and we have 3 branches associated with them. So that means we have 3 currents associated with. So let's write KCL. We have minus I1, which is this current, plus I2, plus that current equals 0. Plus I2, plus this current is simply this voltage divided by the resistance in between. So it's EA minus EB over 1 ohm, and by KCL, that should equal 0. Okay, so this is our equation. Let's say 1. Let's do the same thing. The other node, node B. At node B we have only 2 branches, so that means we have only 2 currents. This current plus that current equals 0. So what we have is EB minus EA over the resistance plus the current of the capacitor equals 0. That's our equation 2. Now these are correct equations, but this is not the correct formulation, because by definition what we want is we want everything to be in terms of formulation variables, which are EA and EB. Plus, perhaps we are allowed to have input terms, and also in addition to input term, we may have some initial conditions, okay, of our dynamic components. So what are allowed are the formulation variables EA, EB in this case, initial conditions, initial inductor currents, and initial capacitor voltage in this case, and finally our inputs in our circuit. Okay, so that's what we want. Express I1, I2, IC, because they are not our formulation variables in terms of formulation variables EA and EB in this case, possibly initial conditions and the input. Perhaps the initial conditions. Okay, so let's therefore use the terminal equations for our dynamic components in order to express I1, I2, and IC in terms of our formulation variables. V1, V2 equals L being our inductance matrix times rate of change of the currents. DI1, DI2. Okay. So the self-inductances are 2 and 7. 2 here, 7 here. And the mutual inductance is 3 Henry. We look at the dots. The first current is entering from the dotted terminal, the second current is also entering from the dotted terminal, therefore the off-diagonal terms will be plus 3. Okay, 3, 3. Okay, now, what we plan to do is, we first multiply both sides with inverse of this matrix. So we will have di1, di2, and then by integrating those derivatives, we will obtain I1 and I2 in terms of the voltages. And then those voltages we will express hopefully in terms of EA, EB, and VS. And then we will have obtained I1 and I2 in terms of our formulation variables. And we will do a similar thing for this guy, the capacitor current. So let's do that. So this implies di1, di2 equals multiplying both sides with the inverse of the inductance matrix, which is 1 over the determinant. Okay, 14 minus 9, that's 5, 1 over 5, and then 7 goes here, 2 goes here, and then you negate the of diagonal terms, minus 3, minus 3. So that's our inverse times V1, V2. And that equals 1.4 minus 3 over 5, same thing, and 2 over 5 times the voltages V1 and V2. What's V1? V1 is this voltage plus or minus, and we can express it easily in terms of known voltages Vs minus EA. Vs minus EA is our V1. As for V2, which is this voltage, it directly equals EA. EA. Okay, so let's call this equation 3. Now, to obtain I1 and I2, we have to integrate that equation. So let's do that. Okay. Integrating equation 3. We have, okay, the integral of di is I minus initial condition. Okay, so what we have is therefore I1, I2 minus the initial currents. I1, 0, I2, 0. Okay, so that's the integral of this vector. And then let's integrate also the right hand side. And in that case, what we have is that equals 1.4 minus 0.6 minus 0.6, 0.4. Then we have the integral of Vs minus the integral of EA, and here we have the integral of EA. Okay. So we have therefore I1 equals I1, 0 plus 1.4 d inverse ES minus 2 d inverse EA. It turns out, if you just write this equation in open form. So that's I1, and as for I2, we have I2, 0 minus 3 over 5 integral of ES, then the integral of EA. Let's call this equations 4 and 5. Okay, and now we have what we want, namely expressions for I1 and I2 in terms of our formulation variables, initial conditions, and also the input. Okay, now let's do the same thing to this guy, IC. And that's really easy because directly from the terminal equation of the capacitor, IC equals capacitance was 3 over 2 d VC. And VC is no other than node voltage B. So what we have is 3 over 2 d EB. That's our equation 6. Now what we're going to do is we're going to combine equation equations 1 and 2, which we obtain by writing KCL, 4, 5, and 6, and in that case everything will be in terms of formulation variables. Now, let's do that. 1, 4, and 5 yields I1, 0, plus I2, 0, minus integral, 2 times integral of Bs, plus 3 times the integral of Ea, plus Ea minus Eb equals 0, which we obtain by substituting that I1 and I2 by the expressions here that we obtained earlier. And let's do the same thing for the pair of equations 2 and 6. 2 and 6 implies Eb minus Ea plus IC, and IC is 3 over 2 dEb. Okay, that equals 0. And this is our set of known equations. Okay, usually we don't leave them in this form. For compactness, we put them in matrix form. Let's do that also here. And later on, that matrix form will be useful in determining the natural frequencies of the circuit. So therefore, it's best to do it as early as possible. Rearranging star yields the following known equations in matrix form, and the structure that we will adopt is similar to the structure that we adopted for the resistant case, namely some matrix multiplying our formulation variables, and on the right hand side we have the terms associated with the input. Now in this general dynamic case, on the right hand side you will have besides the input terms, we will also have the initial condition terms. Okay? And as a generalization of the resistant case, the entries of this matrix will be allowed to contain operators such as d or the inverse derivative or integral operations. Okay. So Ea, Eb, these are our formulation variables, equals something. Okay. So let's fill in the entries of those matrices by looking at our set of equations start. Okay, for the first row, let's get the first equation. What we have for Ea terms, we have an Ea term here, and we have another Ea term here, and that's about it. So we combine those two terms and write 3d inverse plus 1 for Ea. How about for Eb? We have this term here, so that's all. We have minus 1 here for Eb. And whatever remains, anything outside formulation variables, we throw to the other side, to the right hand side, and that yields, for this example, the following. Minus I2, 0, plus 2 integral of the. Doing the same thing for the second equation is much easier. For Ea we have minus 1, for Eb we have 1 plus 3 over 2 derivative operator. Okay, and that's it. We don't have any other terms. Meaning that here this entry must be 0. Okay. Now each of those objects, they have a name. For a simple, this is Yn, It's a matrix that's a function of operators, D and D inverse. This is our vector that contains our formulation variables, node voltage vector. And this is called I and S. This is subscript. So that's the node voltage source vector. Okay. So, the general form that we obtain after formulating a circuit through node voltages is following: Y and D, E equals I and S. Okay. Where Y n of D is called node admittance matrix. E, well, what E is clear, is our node voltage vector. And the right hand side is called node current source vector. So that's about it, about the node voltage formulation. Now let's also look at the dual formulation, namely mesh analysis. For comparison, let's use the same example. Meaning that you're going to formulate the same circuit, this time in terms of mesh currents. Okay. Now, let's, for the sake of completeness, although it's obvious what it is, but let's write the definition of mesh analysis. The method is such that we write down voltage equations, KVL, at each mesh. Okay, in terms of our formulation, variables which are mesh currents in terms of currents. Okay, so let's revisit our previous example. Third order, so plus minus Vs, 2 Henries, 7 Henries, 1 ohm, 1.5 farads, 3 Henry for the mutual inductance, and the currents were labeled as I1 and I2. This is our capacitor voltage, VC. Okay. As before, the very first step is proper labeling. Let this be our first mesh, or mesh A, and this is our IA. And here we have our second mesh. That for second mesh current IB. The directions are clockwise, by the mesh. Okay. So let's write voltage equations at each mesh. Mesh A has 3 branches associated to it, therefore the sum of those 3 voltages must equal 0 by KVL. So let's do that. Starting from this point, we're going clockwise, minus Vs plus the voltage of the first coil, which is V1, plus the voltage of the second coil, which is V2, and by KVL that must equal 0. This is our equation 1. And the other mesh yields, starting from this point, let's say we have minus V2, okay, plus this voltage 1 times IB. Finally, we have the voltage of the capacitor plus VC equals 0, equation 2. Now what we have to do is, because we want to formulate it in terms of mesh currents, we have to re-express these non-formulation variables V1, V2, and Vc in terms of our formulation variables, input and perhaps station conditions. Okay, and once we do that, we're going to put everything into matrix form, similar to what we did with the previous case. Now again, let's start by writing the terminal equation for the coupled pair of inductors. So what we have is V1, V2 equals the inductance matrix times di1. The I2 inductance matrix is 2, 7, and 3, 3. Okay. Now in this case we don't have to deal with the inverses because we have these in terms of currents already, and currents we can express easily in terms of the mesh currents. Okay, so that equals 2, 3, 3, 7, and I1, this current is no other than IA, therefore di1 is dia, and as for I2, it's this current which is IA minus IB. Therefore, di2 is dia minus dIB. Okay. And that's our expression for V1 and V2. It was easy. So let's rewrite them in open form. 5 dia minus 3 dIB is what V1 is. And as for V2, 10 dia minus 7 dIB. Okay, so this is our third equation, which we will eventually use to rewrite the first mesh equation. As for Vc, it's also easy. Vc equals, okay, by Vc we mean of course Vc of t. Vc of t equals Vc 0 plus 1 over the capacitance, and then you integrate the capacitor current. And the capacitor current is no other than the second mesh current. Hence we have plus 1 over C, 2 over 3, then you integrate it. So let's use our shorthand notation for integration, which is the inverse. Okay, of I, C, and IC is IB. This is our equation 4. Now, in the light of equations 3 and 4, let's rewrite the first two equations. 1 and 3. Okay. Yields minus Vs plus 15 dia minus 10 dIB equals 0. Now this is a perfectly valid equation because everything is in terms of formulation variables. Then let's combine 2, 3, and 4. Okay. Right. let's combine 2, 3, and 4, and then we have minus 10 DIA plus 7 DIB plus RB plus the initial capacitor voltage. Then we have the integral term, the inverse IB equals 0. And that pair is our valid formulation equations. Okay, but we don't leave them in that form. We put them in matrix form because it is more compact, and also later on we will use those matrices to compute natural frequencies of the circuit and also some other things. Okay. So let's therefore put this set of equations star into their final form, which is some matrix whose entries are functions of operator D multiplying or operating on our formulation variable vector, which in this case is IA, IB, and that equals the right hand side. And the right hand side is whatever remains once the formulation variables are removed from our mesh equations. Okay, for the first row, let's look at the first equation. Okay, so what we have is for IA we have 15D, for IB we have minus 10D, and what remains is minus Vs. We throw it to the other side, and here we have Vs. Okay, so that's the first row. For the second row, we look at the second equation. For IA we have minus 10D. For IB we have this term, and that term. We have 3 terms. So let's write them down. 7D plus 1 plus 2/3 D inverse. Okay? And what remains is this initial condition. We throw it to the other side, and here we have minus EC0. Okay, so this is labeled ZMD, mesh impedance matrix. This is our mesh current vector, I sub n, and this is BMS, mesh voltage source. So the general form that we want to obtain with mesh analysis is therefore this, some square matrix whose entries are functions of operator D multiplying the formulation variable vector equals VMS. Okay. Where Z and D is the dual of node admittance matrix. It's called mesh impedance matrix. IN is the dual of node voltage vector. Therefore, it's called mesh current vector. This is the dual of the right hand side for the node analysis, and it's called mesh voltage source vector. Okay, it's not really that important what they're called, but sometimes it becomes handy when you try to communicate with other people. Okay, so there's one thing that we also want to talk about, and it's node analysis again, but in a modified form. And why such a modification? might be important, will become clear later on. Okay, so let's talk about the modified version of node analysis. It's called modified node analysis. And the reason that we may require sometimes a modified version is because we don't want integral terms sometimes. And why we don't want integral terms, we will talk about that later, okay? So for now, we leave it as this. So the idea is very simple. What you do is you treat inductive currents as your formulation reference, along with the node voltages. Okay? So augment the node voltage vector by inductive currents okay. The reason is in order to avoid the integral, or in our shorthand notation, the inverse terms. Let's apply this idea to the following LTI circuit. Okay, so it's a second order circuit, one inductor and one capacitor. We have a single source IS, 2 ohm, 3 ohm, 4 ohm, plus minus EC, 3 farads, 2 Henry, and this is our inductor current wire. Okay. We will now try to obtain the formulation for the circuit in terms of node voltages. For that, what we do is first labeling, indicate the ground node, suppose it's a ground node, and then the remaining nodes are 1, 2, 3, let's call them EA, EB, and the third node voltage, EC. Okay, now let's do the formulation, both using the classic node analysis that we have just seen, and also do it using this suggestion, which we name modified node analysis, and then we will have the chance to compare the two outcomes. Okay, so let's go node by node, starting from the first node, node A. Okay. Let's write down KCL minus IS. Okay, this current plus that current equals minus IS plus EA over 2. That's the current flowing through the 2 ohm resistor, plus EA minus EB divided by the resistance between nodes A and B. And that's all. By KCL, the sum must equal 0. Equation 1. Okay. There's nothing, this equation requires no interference whatsoever, because it's already in terms of our formulation variables and input. Then move on to the other node, node B. we have EB minus EA over 3. Okay. This current plus IL plus current over 4 ohm resistor, and that must equal to 0. Plus, now with the classic node analysis method, we cannot write here IL, but we have to express it in terms of our formulation variables and input and the initial condition. So let's do that. IL 0 plus 1 over the inductance, and then you integrate the voltage. Inductor voltage, and inductor voltage is no other than EB. So here we write the inverse EB. This whole thing together is the inductor current. And finally we have EB minus EC over 4, and that equals 0. Let's call this equation 2. Now, modified node analysis suggestion tells us that this is, for some reason, let's not worry about the reason now, this is something unwanted, this integral term. Therefore, leave this thing, IL, as IL. In other words, treat it as one of your formulation variables so that it's allowed now to appear in our equations. So therefore, let's rewrite the same equation, this time leaving IL as IL. 3 plus IL plus EB minus EC over 4 equals 0. Let's call this equation 2 prime. Okay, so this is the equation that we will use for the standard node analysis, and this is the equation that we should use for the modified node analysis. Okay, let's move on to the last node, node C, and write EC minus EB over 4 plus IC equals 0. What's IC? IC is 3 dVc, and Vc is no other than EC. Therefore, we can write directly that current as 3 dEc equals 0. This is our equation 3. Okay. Now we have all the equations that we need for the standard node analysis, namely equation 1, 2, and 3. And all the equations are in terms of the formulation variables, the initial conditions, and the input. But if we go with the modified node analysis, we have 1, we have 2 prime, we have 3. So we have 3 equations, but the problem with that is we have now 4 unknowns, namely EA, EB, EC, and also IL. Since we have 4 unknowns or 4 formulation variables, what we require is a 4th equation if you want to formulate using modified node analysis. And that 4th equation is no other than the terminal equation for the inductor. So let's write that down as constraint equation. Okay, which is inductor voltage equals 2 times DIL. Inductor voltage is no other than EB. So what we have is EB equals 2 DIL. Okay. Since we collect all the formulation variables at one side, it's better that we write this equation as EB minus 2 DIL equals 0. And let's call this equation equation 4 prime. Okay. Now the formulations or the equations are ready, both for node analysis and modified node analysis. So as a final step, let's collect those equations in proper matrix form. Okay. So this is the classic or standard node analysis. Okay. What we have is formulation variables are EA, EB, and EC. So we have 3 variables. That means we need 3 three equations. Okay. And those three equations are 1, 2, and 3. Okay, let's put them in matrix form. This square matrix multiplying the unknown, formulation variable vector equals the right hand side. Here we have EA, EB, and EC. For the first row, let's get the first equation. Okay, so what we have here is for EA we have 1/2 and 1/3. That makes 5/6. For EB we have 1/3. For EC we have nothing. And then what remains is IS. We throw it to the other side and it appears here. IS. So that's the first row. Let me quickly fill in the remaining rows. We have minus 1/3. Here we have 7/12 plus 1/2 integral. And here we have minus 1/4. And we have the initial condition here on the right hand side. And the third equation gives us 0 minus 0.725 and then 1/4 plus 3D, and the right hand side is 0. Okay. And then we have the modified node analysis. Okay, let me write it here. Outcome of modified node analysis will be written shortly. Formulation variables are this time EA, EB, EC, and IL. So we have 4 variables. Okay, 4 variables means we need 4 equations. And those 4 equations are 1, 2 prime, 3, and 4 prime. Okay. And then we will have 4x4 matrix multiplying our 4-dimensional formulation variable vector that equals the right hand side. Okay. EA, EB, EC, and now IL is one of our formulation variables. Okay. From these equations, we easily obtain the entries of this 4x4 matrix, and also the right hand side. Let me quickly fill it in. 5/6 minus 1/3, 0, 0, IS. Minus 1/3, 7/12, minus 1/4, 1, 0, 0 minus 1/4, 1/4 plus 3D, 0, 0, and finally, the last row corresponds to equation 4 prime, which is our constraint equation, coming from directly determined equation for the inductor. 0, 1, 0, minus 2D, right? Okay, here this entry is 0. Now let's compare this final result with this final result. Note that here we have no integral terms. Okay, and whenever you have integration, automatically the initial conditions appear. Therefore, no integration means no initial conditions. Here, no initial condition terms appear. this new vector is called the augmented non-voltage vector. We'll talk about why we don't want the integral terms later.